То есть идеально подготовлено. Вот, но как бы, что мы обсудили в прошлый раз, это про то, как выглядит группа ранга 1. Ну а теперь давайте попробуем. Ну и в частности, что мы как бы уяснили, что если у нас есть тор, ну, Т альфа, субмаксимальный тор, ну то есть как бы соответственно ну вот у нас есть весовое разложение относительно. Причем у нас есть вот как бы группа, которая состоит из борелевских, которые его содержат, и у нас есть, ну, и Т, да, напомню, что это пересечение всех борелевских, которые содержат фиксированный максимальный тор, да, и тут даже жарко. Хорошо, вот, соответственно, мы берем пересечение всех борелевских, мы можем разложить теперь по, соответственно, оставшимся камням. Вот Т-альфа – это субмаксимальный тор, то есть мы зафиксировали это те элементы Т, на которых обращается в ноль как раз альфа. Да, альфа – это, соответственно, мультипликативное характера, соответствующее вот весовому разложению. И как бы, ну, то, что он равен единице, это как раз задает гиперповерхность, да, в торе. Вот, соответственно, мы рассматривали централизатор, это Т альфа, и выяснили, что в группе Ж, да, и если мы его факторизуем в точности по вот этому Т альфа там является центром, вот, соответственно, мы получаем, что это группа полупростого ранга 2. Ну и на самом деле просто ранга 2. Ну, ранг это разменность максимального тора, полупростой ранг это разменность максимального тора фактора по центру. Группа полупростого. И что мы про нее выяснили? Ну, то есть, если G тильда полупростого ранга 2, то есть тут на самом деле, ну как бы у нее, заметим, что у нее может быть, это не просто, ну как бы PGL, да, ну PGL2, у нее может быть какой-то радикал. Но радикал нам как бы не очень мешает, поэтому у нас как бы утверждается, что есть отображение селективное в PGL2. И ну как бы оно приходит, соответственно, с действия, там G действует на G тильда фактор по B. Ну, по B тильда это как бы флаговое многообразие, причем, что мы знаем, что тут есть ровно две неподвижные точки. Причем множество неподвижных точек относительно максимального тора это состоит из двух точек. Да? Соответственно, это точки, но они отвечают элементам группы Вейля. Соответственно, дублевая альфа, да, это нормализатор. Но вот эту группу можно обозначить да, через G альфа, и как раз обозначены они через G тильда. Вот, соответственно.
Сейчас, это же все вроде было про группы полупростого ранга 1.
Да, полупростого ранга 1. Да. Ну, я просто как бы, мы это применим как раз вот эту ситуацию, да, когда мы изучали абстрактную ситуацию, да, по простому ранге 1, но применяли ее, ну, мы будем
Ну, да,
применять непосредственно к централизатору вот этого дела. Вот. Я просто хочу подытожить, что у нас есть, чтобы, то есть мы получаем, что здесь есть W альфа как минимум два элемента, и этот элемент n альфа можно поднять, то есть n альфа можно поднять до элемента, соответственно, z, g, t альфа, и здесь он как бы, ну, я имею в виду, мы централизатор можем обозначить через g альфа. Как раз, и, ну, все равно там факторизуется по центру. То есть мы тут же альфа BT, да, вот, соответственно, вот этот n альфа, он как бы, как он действует на максимальном торе, ну, он, понятное дело, нормализует n альфа, соответственно, Т альфа, ну, на Т альфа это просто тождественное отображение. А если мы n альфа подействуем на, соответственно, Т фактор по Т альфа, это он будет изоморфен GM в мультипликативной группе. И это действие, соответственно, элемент Т отправляет в Т минус 1, да? Ну, представитель. Соответственно, мы получаем, ну, это единственный автоморфизм GM. Не гомоморфизм, а именно гомоморфизмов там много, это у них ядра, соответственно, корни из единицы, вот, ну, алгебраических, а, соответственно, ну, такие только минус единица. И мы видим, что, ну, если с точки зрения алгебры Ли у нас тор раскладывается, ну, как бы ну, то есть у нас конечная группа действует на торе, соответственно, мы получаем, что вот это значение можно отщепить и не на торе даже, а можно как бы, ну, имеется в виду следующее, что, то есть W альфа, она действует на торе, но Тор как бы не очень хороший объект, потому что там есть характеристика, да, ну, может быть, у поля характеристика, поэтому действие этой группы, конечной группы в представлении простой характеристики, но это не очень хорошо по причине того, что полупростоты там нет. Ну, поэтому мы как бы делаем здесь вот этот трюк, который связан с однопараметрическими подгруппами. То есть мы на самом деле альфа, W альфа также действует на решетке характеров Тора, на хи от Т, то есть гомоморфизмы из Т в GM. Или на решетке, можно говорить, что она действует также на решетке, на двойственной решетке однопараметрических подгрупп. Соответственно, наоборот, гомоморфизмов GM в Т. Да, и, соответственно, вот это уже дискретные решетки, они изоморфны Z по N, где N это размерность Тора. И отсюда, ну, сам Тор изоморфен над алгебраическим замыканием на К степени N. Поэтому мы видим, что на самом деле представление W полупросто здесь, и это позволяет вот отщепить вот этот корень из минус единицы. Да? То есть это действие конечной группы. Конечной группы на С, да? На решетке. Линейное действие. Ну, потому что это сопряжение с помощью элементами группы Вейля, это гомоморфизм Тора. Отсюда следует, что на гомоморфизмах, ну, они составляют абелеву группу, поэтому мы действуем линейно. Поэтому у нас есть полупростота, есть вполне приводимость представлений. Ну, на C. Ну и как бы, ну, целочисленность немножко, ну, как бы надо, что так, ну, как бы, уже каплю постараться, но тут уже, как бы, недалеко. Вот, соответственно, у нас, ну, как бы, что происходит теперь, вот, ну, как бы, теперь, если у нас, ну, группа B, которая это элемент G по B, ну, в множестве неподвижных точек, да, вот, она, соответственно, получается, эта группа, она, ну, мы ее можем пересечь, ну, то есть пусть вот, ну, тут давайте b тильда поставлю, ну, как бы, чтобы не, ну, в смысле, что многообразие флагов это, ну, можно просто смотреть на многообразие флагов как на народное пространство, не фиксируя базисную точку. Поэтому, конечно, иногда, ну, говорят, что у нас просто есть, ну, просто многообразие, множество борелевских подгрупп, оно многообразие борелевских подгрупп, которое параметризовано на тильда борелевская. Вот на нем можно посмотреть множество неподвижных точек. Это на самом деле конечное множество, мы помним, да? Конечное для максимального тора, да? Вот, и нашу группу можно пересечь, соответственно, с группой B мы можем пересечь с группой Z-альфа. И, соответственно, ну, как бы здесь тоже у нас получается следующее. У нас получается, что если мы посмотрим теперь, ну, вот это пересечение, это, по крайней мере, мы знаем, что это разрешимая группа, да? Ну, по крайней мере.
Какой Z-альфа?
Ну, G-альфа. Ну, вот, как бы, да, спасибо. Вот. Ну, то есть, соответственно, вот этот централизатор. Вот, но, как бы, да, ну, что тут может быть, ну, с этим пересечением? Вот. Ну, тут как бы мы получили, что на самом деле, вот, ну, как бы ранее у нас была теорема, что если S это, ну, то есть, как бы, давайте я напомню, к сожалению, опять, но если у нас есть S это под тор, вот, то мы показали, что, во-первых, ну, G связано. То есть мы много чего показали. Мы показали, что централизатор S в G, она, во-первых, связана редуктивно. Но если, точнее так, но если G редуктивна, то и она редуктивна, поэтому, ну, эту редуктивность мы, ну, тут не выводили, но мы зато вывели, что если у нас мы берем какую-то борелевскую, которая содержит тор, то пересечение борелевской подгруппы. То есть, ну, на самом деле, что мы показали, что вот это ZT, оно действует на множество неподвижных точек, то есть вот эта орбита ZT на X, где X у нас элементы с G по BT, ну, то вот эта орбита, она замкнутая орбита, совпадающая с множеством компонент неподвижных точек, да? Совпадающих с неприводимой компонентой множества неподвижных точек. Но это замкнутое, соответственно, множество, у которого компоненты дизъюнктно расположены, а постериори мы это понимаем. Вот, извините, только вот так, ну, вот это S. И, ну и вот это борелевскую можно как бы говорить о борелевской содержащей S. Да? Вот, соответственно, да, и опять я чего-то тут с обозначениями напутал. Вы. Ну, хорошо, что я не напоминаю, потому что... Вот, соответственно, мы берем централизатор какого-то подтора, соответственно, берем множество неподвижных точек этого подтора. То есть, в частности, у нас можно брать, ну, множество неподвижных точек относительно S, но оно, конечно, у нас, вот это множество, оно больше, оно, конечно, содержит G по BT. Вот это множество. Соответственно, у нас, если мы берем орбиту вот этого элемента, то она соответствует, это замкнутая орбита, а еще вот это вот множество, оно соответствует тем b, которые, то есть множество b, которое содержит наш тор S. Да? Из-за этого мы получаем, что ну, вот эта орбита, замкнутая орбита, она совпадает с неприводимой компонентой, а значит является флаговым многообразием вот этой группы. Вот, значит, соответственно, B, пересеченная с ZS, это борелевская подгруппа. Это как раз стабилизатор вот этого действия. Вот, борелевская подгруппа. Соответственно, в ZGS. И, ну, для чего я это напоминал? Ну, как бы, чтобы просто, ну, для достаточно глупого с виду утверждения, что это, ну, не пустая разрешимая группа. То есть, по крайней мере, то есть мы получаем, что эта группа разрешима и, ну, и борелевская. То есть, ну, на самом деле, просто, что эта группа разрешима, это очевидно, но мы понимаем, что это борелевская подгруппа из этого предложения в G-альфа. Я хочу сказать, что это, ну, как бы не очевидное утверждение, потому что, ну, мы понимаем, что мы можем борелевскую высечь. То есть, если у нас есть большая объемлющая группа, в ней есть, ну, в ней есть маленькая подгруппа H. В маленькой подгруппе H есть борелевская. Эту борелевскую, понятно, можно делать, поместить в борелевскую большую группу, просто из теоремы о сопряженности, сопрягая борелевскую большую. Да, отсюда можно, ну, мы обычно маленькую сопрягаем в большую, но можно и наоборот большую сопрячь так, что она содержала маленькую. Из этого мы будем получать, что любая борелевская, она содержит на самом деле Давайте это еще раз напомню, просто чтобы было понятно, что это неочевидное утверждение, что замечание, что если мы просто G содержится какая-то H, и здесь есть BH, барелевская, то существует, ну, тут была барелевская B, но существует G из B, из G, да, такое, что GB, G минус 1 содержит BH, ну, просто, как бы, да, это у нас так сопряжение на BH, так, ну, в смысле, мы BH обычно сопрягали, чтобы попасть в B, но тут B, да, такое, что, и это означает, что, ну, если мы возьмем вот эту вот B тильда, то есть B тильда пересечем с H, это, ну, во-первых, она содержит BH, а во-вторых, тоже разрешимо. Но также разрешимо как подгруппа, ну, как подгруппа в разрешимой B тильда, но отсюда следует, что B тильда пересеченная H барелевская. То есть мы видим, что этот выбор, ну, он непроизвольный, его надо подгонять. Но здесь это автоматически. Мы исходно взяли B, да, из множества, ну, вот это B, оно взято в множестве бета T, которое сидит в множестве бета T альфа, да, и как бы, ну, мы уже подогнали просто вот этим выбором. И, но это не очевидно все равно, как бы это мы еще дополнительно вот воспользовались этой теоремой, которая за нас эту работу и сделала. Вот, соответственно, это барелевская подгруппа, и у нас не осталось, ну, как бы, если мы ее возьмем редукцию по радикалу, то есть, если мы возьмем ее образ при гомоморфизме G альфа, ну вот, фи, где фи вот у нас как раз тот гомоморфизм, который G альфа отправляет P GL2. Мы знаем, что он сюрреактивный из прошлого раза. Ну и значит, как бы мы помним, что если у нас есть сюрреактивный гомоморфизм барелевских подгрупп, то барелевские переходят в извините, сюрреактивный гомоморфизм групп, да, то барелевские переходят в барелевские, то в импотентный радикал в импотентный радикал. Поэтому фи это, соответственно, барелевские в PG2, которых, но которые еще также содержат, то есть содержащие образ Тора фи от Т. Ну, образ Тора, он изоморфен, как раз это одномерный Тор. То есть это фиксированный одномерный Тор, тем самым в PG2, вот, который, соответственно, ну, изоморфный Т-фактор по Т-альфа. Ну, вот Т-альфа лежит в ядре вот этого фи, да? Вот, ну, как бы, дайте, да, напишу, что Т-альфа это Т, пересеченное с ядром фи. Вот, ну и мы видим, что, как бы, что здесь, ну, поскольку это одномерное многообразие флажев, есть только два предела, поэтому есть только, соответственно, ну, если мы зафиксировали какую-то исходную B, то есть у нас есть группа B альфа и B альфа минус, да? Ну, в PGL2. Соответственно, как бы, то есть мы берем наши группы из вот этого Тора, пересекаем, и мы получаем только две опции. Да? Соответственно, как бы вот это вот, как бы, чем характеризуется вот эта группа. Но если мы теперь зафиксируем однопараметрическую подгруппу, то есть давайте фиксируем лямбда, однопараметрическую подгруппу лямбда с чертой в t альфа, фактор по t, да, то мы увидим, что у нас есть два предела. То есть b альфа соответствует одной неподвижной точке.
Что такое t альфа фактор по t? T же это
О,
больше.
t фактор, извините, да. То есть b альфа соответствует одной неподвижной точке. Ну, на p1 изоморфный g альфа по b альфа. Да? Да, давайте вот это еще с черточками обозначим, что это, ну, как бы они уже в PGL, то есть самые глубокие. И b альфа минус, то есть соответствует, то есть как бы но когда у нас уже фиксирована однопараметрическая подгруппа, у нас есть два предела, в плюс и в минус, да? То есть буквально у нас однопараметрическая подгруппа, она уже имеет направление, да? То есть это элемент в решетке, в z степени m, да, и как бы это именно вектор, да, есть однопараметрическая, есть минус однопараметрическая. И вот это b альфа можно считать, что это предел однопараметрической подгруппы. Но если мы берем общую точку p1, то это предел при лямбда, стремящемся к нулю. Вот лямбда t, y, где y общая точка. Вот. Yeah, sure. I mean, in Russia you may always come in. It doesn't. I would say that we have a democracy, so as there was a very nice, a very nice phrase of Parshan when the seminar went too long. So I won't name the speaker, so not that long. But it was very long and very nice talk by him, but it went too long. I mean, more than maybe 2 hours, and even for Shefarage seminar, it is too long. And so the person has asked, clearly understanding that he went completely over time for many, just for as much as he could. He asked how many time do I have is left for me. So Parshan has told him that we have democracy. You speak whatever time you want, but we listen whatever time we want. And then in a few minutes he got a call and he left the room. So at least, actually I remember him returning, but it was a very nice phrase. I really remember it. Yeah. So you have this B alpha, this corresponding correspond to the limit going to infinity. Lambda goes to infinity. And now I want to so this actually so this cuts our set, of course, into subsets, yeah. But notice the following observation, that you still have the element. I mean, it's not just decomposing the set of two into abstract sets. I mean, if we without any additional structure, this set can have. So I want to say that we can now decompose the set of Borel subgroups. So is decomposed into two sets. So that B with property B, so B intersection with 5B intersection with, and of course, I mean, you may consider B alpha, which is pre-image of, this kernel has a radical inside, so if you take complete pre-image, it will be also Borel subgroup. Yeah, so just so put B alpha to be pre-image 5 B alpha. It is also and B alpha inverse B alpha minus to be a phi inverse B alpha. So also Borel subgroups of G alpha, since kernel of phi is solvable, solvable. So you have so it is decomposed with now our set is decomposed into two subsets. This is one with the property that you have B alpha in the intersection, and the other has property that you have B alpha minus in the intersection. And of course, I mean, these two subsets a priori can be different size. Yeah, but why did they have the same size?
Well, I suppose we can compute their size because it's
no. No. You have an alpha here, additional element. What happens if you conjugate an alpha, this B alpha? Yeah? You will have opposite group. Why? I mean, this is again not clear, but we have this kind of characterization with limit. Yeah. So notice that conjugation. So, третья, да? So this is due to the following. So an alpha acts as T in, or as T maps to T inverse on T modulo T alpha. This shows that it changes the limits. Yeah. So this implies that in particular an alpha on lambda T is just lambda in T minus 1. Precisely it is. I mean, it is just rewriting. And this interchanges limits. Lambda T goes to 0 to lambda T goes to infinity. And you have I mean, notice also that y is generic point of the subset. So I mean, of course, we should take y in y0 in the complement g mod p tilde without fixed points of lambda. So g alpha. Yeah. So without fixed points of lambda t, and this set. I mean, this was characterization. I mean, of course, the point is different, but this is still, I mean, then n alpha 0, y0 is still in this subset. So it's still in the same subset. So this allows you to decompose your one parameter subgroups. Yeah. So yeah. Also. Yeah, so there is some refinement of. So notice that this is so this is still some kind of reduction. We took this kind of reduction of T modulo T alpha, but one parameter subgroup can be taken inside T. So and we can ask the questions. So we can ask the question. In more general setting. Yeah, and actually, yeah, so I wanted to say that this decomposition into subsets is not surprising, yeah, because we have a bijection between the set of Borel subgroups containing T with the fixed points in G mod B mod T, yeah. And in G mod B T fixed points, and this corresponds to the elements of the Weil group. Yeah? And if you take an alpha, you have so these two things corresponds to two cosets. So this is I mean that you have a subgroup of two elements, and you have one coset corresponding to. Нет, сейчас. Не то. Не, просто, ну как бы, просто два подмножества. Yeah, so. Yeah, so then just we can ask this question in more general setting. And we shall understand what is regular subgroup. So in order to do it, so take representation of G, so such that G mod B is contained in P of V. It is an orbit of B fixed vector, and let us assume additional conditions. So so assume that G mod B is not contained in a hyperplane of P of V. In any hyperplane H inside P of V, and this is a rather strong condition. Otherwise, because otherwise which it is equivalent. I mean, this is should be equivalent to some representation theoretic, very simple property. Yeah. Чему эквивалентно, что вот ну, это вообще для любой орбиты, если орбита не содержится в гиперповерхности, гиперплоскости или просто подпространстве линейном, да, то is not contained. Да. Вот. Because so otherwise what you can consider, so G mod B, it is an invariant subset. So G mod B is contained in the intersection of GH, where G runs through the element of the group G. And this is submodule. So submodule, G submodule. G projective subspace, but it corresponds to, I would say that H is just a projectivization of some subspace. Yeah? Ой. Так. So this is equal to intersection of, yeah, so P of W and intersection of GW. G is invariant linear subspace. Linear subspace. So a representation is simple. Yeah. G module. And if you remember the algebra properties, so let me recall representations of the algebra. So this is just recollection in order to have some sufficient intuition what we're doing. I mean, of course, we will be working in the setting of algebraic group. So, but representation theory tells us theory of the algebras. It says that so that I mean, if you have any representation. So any representation, you have at least, so here you have V lambda, B fixed, B invariant vector. So by Lee-Colchan theorem, S will be semi-invariant vector. And you may generate a submodule by this vector. Yeah? So you may consider G of V lambda, and this is from the viewpoint of the algebras. You can consider this set. Yeah, so notice that this is a linear span of the orbit, yeah, and this is just a tangent space. So this is sorry. So yeah. So you can consider one application. This is tangent space. Yeah, but this won't be invariant under the action of Lie algebra because Lie algebra acts via commutator. And if you apply to this subset additional psi via representation, it won't be so this is not G invariant subspace. point is tangent space to the orbit. Yeah, because from the viewpoint of tangent spaces, yeah, so you have application of G to V alpha. If you conjugate, it will be a tangent space in the other point, corresponding to G V alpha. Yeah? So, and I mean, when you move it by G, they move to. So they are tangent spaces in different points. So this tangent space is not the invariant subspace actually. Yeah? So and in order to make it, what we have to do in order to make it G invariant subspace? Apply all possible Lie algebra, subsequent, we have to do subsequent applications to Lie algebras. We have to take representation of Lie algebra, the corresponding matrices, and to make subsequent applications of them. And this is precisely universal enveloping algebra. So this is invariant algebra. Formally, because I mean, just our Lie algebra act on the vector space via associative algebra. We have to take representation of Lie algebra, yeah, and so we're putting G inside GLV, and then we act by representations by matrices here. And so this factors through the universal enveloping algebra, and what is generated by the all possible applications of matrices, it is precisely what is generated by universal enveloping. And but V alpha is be fixed. So if you take so formally you can make a map of smaller subset. So just take the universal enveloping of B that acts, so V alpha is UB module. So KV alpha, the linear span of V, is U of B module. So module. And notice that you have Poincare-Berghoff-Witt theorem. So if you recall that you have this kind of decomposition of torus and G alpha, so E alpha and E alpha minus. I mean, this is for reductive group. Just F alpha is just E alpha minus. Yeah. So you have so E alpha act trivially on V alpha. So you have actually Poincare-Berghoff-Witt theorem that this is so associated. So you have the filtration spanned by monomials, and so here you have this can be written as tensor product of as modules, yeah. So as U of T modules. So U of B and U of U, and U of minus. So this generated by E alpha, and this is generated by U E minus alpha. And then just
Какое? Седьмое.
А b это же у нас будет, вот b красивое, это же у нас просто будет тор плюс e альфа, да?
ну, линейная комбинация я, да,
Да,
да, давайте напишем, что b это просто тор плюс как раз. So this is the alpha, where alpha belongs to delta plus, and delta plus is, the choice is very easy. You just have root system, and it is not a special choice, I would say. It is just taking any hyperplane. So you just take delta plus to be in the subset of the linear function is larger, strictly larger than 0, and it's not vanishing on the roots. Yeah, so L alpha is not equal to 0 for any alpha. And we are actually, so this linear function from the viewpoint of the lattices now in the torus, it plays role of one parameter subgroup. The characters lives in one lattice, and one parameter groups lives in the dual lattice. And the choice of positive and negative roots is just a choice of pairing with this one parameter subgroup. And we want to express it in terms of limits in order to understand the properties. I mean, without introducing root systems and this. And checking something about roots, we want to re-express it in terms of algebraic roots. And so here I wanted to give some kind of motivation. So as a linear subspace, so U of G as T module, as U of T module. So this is isomorphic to U of U minus applied to V lambda. So and you will see that this corresponds to the application of monomials of the form E minus alpha, E minus k to V lambda. And this is T semi-invariant vector. Just you have to do a direct calculation via commutators. Yeah, so with weight, lambda minus the corresponding sum of weights. Yeah. Yeah. Okay. I mean, this is just the calculation that you have E alpha, so you apply it to the vector y of chi, and you apply h alpha, h to it. Yeah? And the commutator of h is just, so in the representation, you can change it to E alpha h plus commutant of h of E alpha, E minus alpha, yeah? And this commutant is just minus twice, so minus the pairing of h and alpha, yeah? So the pairing of alpha to h And this is so you applied to chi, and this so h applied to chi as so e minus alpha. Yeah, sorry. So I have forgotten the minuses. So this will be just so h applied to v chi as chi of h times e minus alpha v chi plus this minus alpha of h e minus alpha v chi. So this is just chi minus alpha h e minus alpha v chi. Yeah, so a very simple calculation via commutator that shows you that the weight is decreased. But this means that since you have so since L of alpha I is strictly positive, yeah. So this means that L of lambda minus alpha 1, etc., minus alpha k is strictly less than L of lambda. So this will show you that your after the choice of the Borel subgroup. So this give you the choice of this linear function. The weight becomes extremal. So all weights have smaller value, strictly smaller value. So this means that there is only one highest weight vector in this module. So so that there is unique weight, so a unique vector of weight lambda, so unique vector of weight lambda, or better to say chi, yeah? I mean, I shall put chi everywhere here if you don't mind. So, so with chi in the and here I can put chi tilde, yeah, for this calculation. Yeah, so there will be unique vector of weight chi in the module U of G UB V alpha and V chi. And this means that in any image of this module, yeah? So this means that in any image, so this is called Verma model. So yeah, by the way, it is the question to you. What is right stress for Verma? So there is a famous Indian mathematician, Verma. Yeah, so I mean, you pronounce it Verma. Yeah, yeah. So thank you. Yeah, because in Russian, I mean, since Russians has met this name is only written in Soviet times, more or less. So they read all the stresses that are logical to our language, possibly as every person do. Yes, so some people call it Verma with not right stress, and I was really surprised when I went abroad to the conference that the right stress is Verma. Yeah, so so Verma module. So you see that I mean you have to note that it is infinite dimensional. But when you map it, so it is infinite dimensional. But so here it maps to UGF. V lambda, V chi as a submodule in V, so submodule. But again, as we have seen that in any image of linear map, of G linear map, so image of G modules, yeah? In any image of homomorphism of U G modules. Better to say like this, yeah? So, and in particular of G modules. So this implies this property that a chi is extremal, and if V is so when V is irreducible, then V chi has multiplicity 1. Yeah, so there is only one way, vector this way. And we have to show this, let us show it directly by our observation. So let us show you this statement. So claim. So if you have G mod B in the P of V, where as an orbit, so G mod B is isomorphic to G V lambda, V chi, the subset P of V, such that just B is not contained in any proper subspace. And then there is a unique point vector of weight V chi. Yeah, so I have noticed that so if you have that any module, if you have B fixed vector, so in any module you can find B fixed vector, and when you find B fixed vector, the linear span, the G linear span of this B fixed vector is just image of this thing, of the Verma module. Mm-hmm. And since in Verma module we have noticed that V chi is the only vector for this highest weight V chi, then in the image also there is only the multiplicity is preserved. I mean, it is as a zero preserved. But we noticed that if you take the vector and take the linear span, then it is not zero. So you get a submodule, and if V is simple, it has precisely a multiplicity. So it coincides with this linear span, and V chi has multiplicity 1. So since G V chi coincide with V. So, and I want to prove analog of the statement for just this in this setting. However, there is slight difficulty that I mean here where if you do not use the algebra decomposition and you do not want to use it, I mean it's fun that to see that this statement is actually easier to introduce than to introduce all this machinery. But of course, we do not understand what is VCAT. Yeah? But we can take, we can start with regular one parameter subgroup. So take regular. We shall find a stronger statement actually. Yeah? So let us take regular one parameter subgroup. And we shall take the limit. Yes, so with respect to this subgroup. So suppose it has weights. So let us take weight decomposition. So lambda t act on V, and you have this corresponding decomposition into the spaces, and you have so let us put them in the following sequence. So I mean the following. So we have decomposed VMI in the corresponding weights of yeah. So let us just decompose it in the refined. I mean in one-dimensional spaces. So this will be one-dimensional subspaces. So this is not canonical decomposition, right? Because it's not the composition in the weight subspaces, it is a choice of basis. So this is a choice of weight basis. So maybe I would better to say like this. So this is weight basis. And I have decomposed the vectors with the same values here, and then with higher vectors. And if we take such vector, so V in this decomposition, sum of lambda I V Mi, then the limit, of course, of our one parameter subgroup in this space, lambda T tends to 0. Yeah, so this will be here just tends to infinity. Yeah, so this will be just of lambda T V. So if you just take the limit and the projective space, this is just the sum of the vector V up to so lambda. So better to it's not good to take to denote linear combinations by lambda, since we use lambda as well. So this is AI V Mi. Yeah, where I is less or equal than R. Yeah, so that we're taking these equal values, and you are taking some up to this highest to equal value. Yeah. So what I want to say that of course. So suppose you have a point. So suppose without loss of generality. That V1, yeah, so the first VM1 belongs to this set of belongs to the flag variety. It's clear that it is fixed. Yeah, but so yeah, and so I claim that other multiplicities is equal to 1. Yeah? So we claim that other multiplicities is equal to 1. But notice that you can consider so we claim that the family of points, so family of points of this form, of the form V1 VM1 plus mu VM2. Yes, let me put some parameter. Mu will be VM2 plus etc. They should they appear in G mod B for infinite number of mu's. So appear vectors of this form. Yeah, so with mu not equal to 0 appear in G mod B for infinite number of values of mu. Otherwise you just we need only to know that we have infinite possible values of mu. So since otherwise, G mod B is covered, is contained in the union of hyperplanes so defined by the coordinates, so corresponding coordinates z1 times mu is z0, yeah, times mu is, well, z1, yes, we start from 1, is equal to z2, so where, so z1, etc., z2, etc., homogeneous coordinates. But no, we know that G mod B is irreducible. Yeah? Is irreducible. So that there should be and not contained in any. So it will be contained in one hyperplane. One of them. Contradiction. So you have, so we cannot cover them by the hyperplanes, and now the possibility of taking limit.
It's 12. It should be 12.
Да, спасибо. Я прям, ну да. Ага, молодец. And this, yeah, so notice that after that, I mean, if there are infinite number of such mu's, then, so if there are infinite number of mu's, number of values mu, so we have infinite family of fixed points of the form V M1 plus B VM2 plus etc. plus B VMR, yeah, BR VMR. Yeah, so that depends on B. Yeah, so we have this parameter. Other coefficients we do not care about them, but we end at MR, and so just by direct calculation we have infinite number of fixed points. Whenever you have V inside G mod B, yeah, so we know that limit when lambda tends to infinity, lambda T of V belongs to the fixed point set of lambda, and this is precisely the family of points in the set. Yeah, so that your each hyperplane, so you distinguish the points by different hyperplanes, and that's why so they lie completely in the different hyperplanes. However, this hyperplanes they really do intersect, but the set that each fixed point. So I'm writing down in coordinates, but in order to explain what is going on, yeah? So you have the common intersection of the family of hyperplanes, which is of course, so this is one parameter of family of hyperplanes, so they have intersection of projective space of n minus 2, yeah? But we claim that, so I just want to illustrate geometric picture, but this family of points of this form, yeah, they look like this, yeah? So this is projector. So this is actually, this is a curve, yeah? So it intersect, so it's not straight line, possibly, but this is a curve. It could depend on the value. And the one parameter subgroup, so the limit looks like it goes not to the common set of the intersection, but in the opposite direction that do not intersect. I mean, and this that's why they're still different. So they're somewhere just they go to the limit, and the limits are still different. I mean, I just wanted to say this illustration since the proof is too dull, I would say, too easy, actually, from yeah, so this, yeah, now we can consider, so after that we can consider, so open subset Yeah, so now, sorry. So now we can consider open subset of G of B. Of G mod B. So containing this, so now your thing looks like this. So it looks like yeah. So maybe I should say something additionally, that now we have the sequence, so M1 strictly larger than M2, etc. So as for other weights, I do not care about that. Yeah? But the first weight definitely has this strict inequality. So this really tells you that the complement is defined intrinsically. Yeah? So this means that this complement W, so I mean complementary subspace, which is a sum of V Mi, where Mi is strictly larger than M1. So this is the sum of all isotypical components that do not contain is a typical component of psi I, so this is canonically defined. Defined vector subspace, T invariant. Yeah, notice that M1 is it is invariant of with respect to lambda, and lambda is regular, so it has the same centralizer as T. So lambda T invariant or lambda T invariant subspace. So you see, and this implies that yeah, so this implies that we can consider G mod B, so open subset, which is just the complement to the subspace. And on the subspace, the vectors are of the form in this U0. They are of the form precisely V1 plus remaining vectors. Yeah? So we just do E2, EK, where this coordinate is non-zero. Yeah? So I can put it equal to 1. So this, yeah, so of course, yeah, so I wanted to renumber it, yeah, so to renumber it via VI, yeah, so just for simplicity of notation. Yeah? So this means that in the set, so in U0, there exists a unique fixed point. There exists unique fixed point in G mod B. Yeah. Just in so which is fixed lambda point, lambda t point, precisely corresponding. Yeah, because so generally So so if you consider these types of vectors, so the fixed points are precisely semi-invariant vectors, but v1 and the other vi's has different weights. So if the point is fixed, so since the point is fixed, is lambda t fixed. It is v lambda t of v is just m for some m. And on the if v is on this form, so lambda t of v is just m1 v1 plus a2 m2 v2, etc. And this is basis, yeah. So and m1 is not equal to m2, so this implies that ai is equal to 0 when I is bigger than 1. Yes, I want to say it explicitly. So there is only one fixed point in T, which is v1. So we have, and this is specific choice of Borel subgroup. So we put b lambda the corresponding Borel subgroup to this fixed point. Yeah, so this allows us to make this kind of decomposition, and then we can do the following. So yeah, so maybe let us do the break, and after the break I shall explain how decompose. So the analog of the Weil chambers. Yeah, so that now we shall explain how to just while chambers will be in the correspondence with the groups of this kind of form. So let us take 10 minutes break, make sure. А у меня тут что-то накрылось? У меня что-то накрылось?
Нет, я
Вы
поменяла.
позаботиться пришли.
Я поменяла стилус.
Ага,
Вот тут прям
спасибо.
это старый забирает, новый и пишет на новом. Это все.
Спасибо. Yeah, so, so what we get so far, so that we have so notice to that that now we have decomposed the set of set of one parameter, regular one parameter subgroups. So, какой приятный маркер, ну, в смысле, stylus. So, regular one parameter subgroups. It is decomposed into the following subsets. So that yeah, so to is decomposed via the following associations. Yeah, so to lambda we can associate b lambda. Yeah, so that the subgroup. So notice that this kind of limit occurs on the open subset. Yeah. So for each lambda you can say that what is b lambda. So such that it is just a limit point of lambda t, where the limit point, so whatever you like, so it tends to 0 or to infinity. So notice that if you are speaking about the positive, if you want to speak about larger values, then you have to take the limit to infinity. Yeah. So you are taking the limit of lambda t of y, and this is corresponds to y 0, which is so on the set of Borel subgroups, and this corresponds to this b lambda. And since such a limit point exists for open for y from this open subset space, from y from the open subset u 0. Yeah. So you have so for each lambda, yeah. So we have understood that you can associate the open subset, and if you take the point from this open subset and take the limit, there will be concrete limit. So this means that this limit will be Borel subgroup, and this allows you to. So of course, for each lambda, there could be its own open subset. Yeah. But notice that this is just the corresponding. So this open subset is just the. I mean, it is it's unit.
Не буду обращать.
Да, сделаем вид, что ничего не произошло, и слушатели как бы, ну извините. Вот. То есть отнесемся к слушателям в эфире с особым цинизмом. Да? Вот. Вот. Приезжайте с Франции. Да. Вот из ваших Франций. So if you take this lambda t, Yes, so that you will have a limit precisely in this point corresponding to V1. However, if you take this closed subset, still, so each, lambda always has a limit, and in any direction. So here, this means that there will be its own limit for lambda t. It could happen that it is inside the other point. And there will be the corresponding strata. So this means actually that, but this B lambda is well defined because there is only one open subspace with this property. Yeah, so that since such open subspace is unique, subspace U0 is unique from connectedness, from irreducibility of G mod B. So there is a unique way to associate this lambda. Notice also that so for actually this open subspace, yes, so we have considered U1, and so we can consider. So we can notice that you have G mod B, and you have the set of fixed points, and it corresponds to the collection of vectors. So V1, V2, etc., Vk. So from what we have proved, yeah, so we have proved that we have proved that if they are the limits of one parameter subgroups, they are of multiplicity 1. Yeah? And if they are of multiplicity 1, then you can just, they are also weights, they are also weight vectors for torus. For maximal torus, because lambda t is regular. Yeah? And this means that this implies that we can consider open subset, can consider the only V1, VL that are limit vectors of one parameter subgroups as before. And take a common open subset for all one parameter subgroups. So U0 is just V1 not equal to 0. I mean, so it's just put them in the common basis. Put V1, VL into clear basis. And U0 is just Z1 not equal to 0, etc. ZL is not equal to 0, so it is a common open subset. So common open subset for all one parameter subgroups. Yes, so that I mean, knowing this, I could even do this argument easier. So you just, for one parameter subgroup, you just take the point from this open subset and check what is the limit. So also as a corollary, so while group, so you have this association, so you have the corresponding decomposition. Yeah, so this set of lambda is decomposed into morally, yeah, so that geometrically this happens as follows. So you have a root system. And you have, however, notice that so here we are proving slightly weaker because I do not say that each point of G mod B, each T fixed point can be reached by one parameter sub. Yeah, but notice that a posteriori, since while group is acting transitively, so this is true. I mean, whenever you find one such point, so note that, so as a byproduct of the proof, so since, so note that since WT act on the set of regular one parameter subgroups, yeah, so maybe I would act on the set of fixed points transitively, simply transitively, even simple transitively on the set of G mod B, simply transitively. So without kernel and mapping each point to each one. Yeah, so if V1 is so V1 is fixed, so limit point for lambda. And then if V is just W1, so it is limit point is limit point for W lambda, W. So you see that actually this is the description. So you have these points are in this external set. And moreover, you can also, so notice that this is a corollary of very, I mean, these were highly non-trivial theorems. I mean, not evident, but we get all a posteriori, all the machinery, all about the root system we want to obtain. And now we can even see what is positive, what is negative. So now we can distinguish the following. So if you have just now we can choose B equal to B lambda 0, so such that lambda 0 alpha is strictly B. So we can take the root, yeah? So we can take one parameter subgroup which is positive on this root. And then we can define B alpha to be an intersection of centralizer of S T alpha and B, yeah? And also notice that you can so there will be an opposite. So this has image precisely B alpha. So just B alpha overline in PGL2. Yeah? And then we can say that B minus alpha, B minus alpha is just the conjugation. So so you have this canonical element corresponding to the element of the while group, yes, so in the centralizer. And that acts as inverse. And this, you see that this is precisely, so image precisely B alpha inverse. And this, since n alpha changes the value, yeah, so notice that it in the quotient, yeah, so you have the hyperplane, and so the hyperplane alpha equal to 0, so that defines the corresponding torus, yeah, in the set of one parameter subgroup. So if one parameter subgroup is here, it has a fixed point B alpha. If one parameter subgroup is negative, so any negative one parameter subgroup, so which is minus lambda modular the modular the subspace lambda equal to 0. Yeah? So it will be a limit via alpha inverse. So which is so you will have the decomposition of groups so you have B that corresponds to B alpha and N alpha B N alpha inverse that will correspond to this kind of intersection, and this will result into the two opposite subgroups in PGL2, and this can be checked. I mean that you have either this type or this type. This can be checked via the pairing of lambda with alpha, since I mean this is a limit in one direction, and this is a limit of lambda in the opposite direction. So in order to this correspondence is consistent with limits on G mod B and G alpha B alpha, and this actually this is a subset of this one, yeah? And so that's there is a direct consistency. So in order to check that something is here or something is here, you just check the sign of in the quotient. So to check the key A or B, we have to check image of lambda in T mod T alpha, and this is checked via the pairing with alpha. So this is a sign of pairing with alpha. And now I want to just say about the radical and prove that the radical is just intersection of Borel subgroups containing T, unipotent part of the radical. So, and this will be so what we are doing, this is so from this we will one can derive even Breuer decomposition, so that we will use, and we shall derive it a little bit later. So after that I want to discuss some kind of geometric invariant theory, and whenever we shall need Breuer decomposition, so we shall also recall about that. So theorem that, so we have again introduced T, let us recall that it's intersection of B, T is contained inside B. Yeah? So the claim that unipotent radical of G is just this group unipotent radical of this group. Yeah. So notice that there is a trivial inclusion. Yes, so because this is clearly yeah, so there is of course trivial inclusion. Trivial inclusion is the following, that just argue. So since argue G, it is so in the radical it is the set of unipotent elements, and you can, so since you can write down radical of G as the intersection of Borel subgroups, just B is the Borel. Without any conditionless. So this is just intersection of maximal corresponding maximal unipotent. So this set is clearly, and this is fixed set. Yeah, so clearly you have this set is small, so this is evident.
Yeah.
So far.
T is fixed.
Yeah, T is fixed. Yeah.
It's
So
something
the
torus.
yeah. So T is fixed. That's more torus. And so you have an evident conclusion in this set. Yes. So it was important to speak about the roots of. Notice that these are this group corresponds to the roots that are in the Borel subgroups containing T. So this was important um, uh, to our yeah. So you have this kind of root decomposition. So first of all, you have big root decomposition. Yeah? So which is a complement to the Torah. Yeah? And just a second. Yeah, so you have this complement to the torus, and this you have also complement to this Lie algebra of this group. Yeah, and this notice that this should correspond to the so since this is a unipotent radical, so for that a posteriori we want to establish. So this is the real root system that we want to study, that corresponds to the structure of reductive group. So this is a subset. So lambda sits in psi, and that's why we have considered the centralizer. So notice that we have considered just T alpha only for the roots of this form, and not for the general roots. Because only for the roots of this form we could say that, consider T alpha where alpha of T is equal to 1. Yeah, so for this we argued that since alpha is not inside I of T, yeah, so just in this G alpha is not inside of I of T, the group, the centralizer inside the G of T alpha is not equal to the centralizer in the corresponding parallel. So that was an important observation. So otherwise the root will be, so if this happens, yeah, so this would this B will produce the yeah. So this will imply that the root. So then alpha will be in the set I of T. Yeah, so that this actually a priori this is possible for this equality for the corresponding elements from I of T, and we have argued that so if you take the roots which are not from I of T, this is not possible. And then you now let us just recall some yeah. So what we should do? Yeah. So now we have to notice. So it is enough to show to show that actually that I of T is just normal subgroup. That I of T is normal in G, yeah, because I mean this. So if I of T will be in the intersection, then this will imply that we will just imply that GIT G inverse it is equal to I of t, and this group is contained in the intersection of Borel subgroups conjugate. Yeah? And by using conjugation, we will obtain, of course, all sets of Borel subgroups. Yeah? So B inverse runs through all the set of Borel subgroups. So you will have the corresponding conclusion. Yeah. So now, if you want to use this kind of normalization, so G, so notice that we proved that G is generated by all subgroups, Borel subgroups, containing P. Yeah, so that was a lemma. Yeah. So it is. We can check this normalization. So in order to do it, so we can check this kind of property for just for any Borel subgroups containing this fixed. So we have to prove that I of t. So we have to prove that I of t is normalized by any normalized by any such subgroup. Yeah? By any B tilde contain. I mean, this is still will not be a free proof, but this is some kind of additional reduction. So from the beginning, you can take B. Yeah. So just we need to prove that I of t is normalized by B. Yeah. Normalized by any. So in particular, yeah, so just put B tilde equal to B. So then you want to understand what how your so how you generate B. So B is generated. So B is generated. So claim that B is generated by the set of centralizers. So centralizers in B, of course, of S, where S S runs through codimension 1 subtor. So there are many subtoruses here. Of course, there could be regular so here there could be a regular subtori and a singular subtori. Yeah? So of course Yeah, so um, yeah, so suppose you have now you have to check the following. So you have Borel subgroup, and now you can take Lie algebra. Yeah, so in order to understand, to compare two subgroups, yeah, so we can take the group generated by centralizers. So let me put the formula. So let B and you take the subgroup generated by centralizers. Yes, of codimension 1 torus in P. So this, yeah. So now, if you have two subgroups, you can compare them by considering. Yeah. So of course they contain T clearly because this group contains T. Yeah. So they have weight. You can compare the Lie algebras. So we can compare. Algebras. And so that means that B and A. So since the centralizer is defined, in order to understand that the groups are equal, you can consider the tangent spaces, and this can be done via consider. So they have T-weight decompositions. Yeah, so they T-weight decompositions. And this. So if you have then this is clear just because if you have you're considering G alpha, it is a subset of B. Yeah, so notice that this corresponds to as we have said that so either it is contained in I of T and I of T is so this means that just vanishing of alpha, so alpha is equal to 1, it is precisely a codimension 1 torus. So codimension 1 torus. So this is just, this is nothing. This is not the condition. Yeah? So just now we have to just you have two cases. I mean, if your S, so still your S can be the codimension 1 subtorus obtained as that. So this is proved. That then we have to consider. So now consider the normalization. So proof. So notice that I didn't say that I have. I have. Made a special class of Torah. Yeah, so we have considered the central. In order to introduce reflections, we have introduced a special class of codimension 1 tori, which are just correspond to the roots outside of ET. And but then you in this proof I didn't state that the root G alpha is outside of I of t. So this is just considering two cases to include the G alpha in the centralizer. So we can consider codimension 1 torus here T alpha, just I would say S, defined by this kind of thing, and G alpha is contained in the centralizer of GS. Yes, so I wanted to say the following in this part. But then you have two types of roots. So we wanted to have the roots corresponding to reductive part and to the radical. And here we have two cases so that are possible. So the root corresponds to lie in I of t, or it lie in the modular I of t. Yes, in the outside I of t. So now we have to prove normalization. So prove that I of t is normalized by B. So here you have two cases when S is a codimension 1 torus. But there are two options. If it is regular, so regular, and this, saying that it is regular, we get that, so centralizer, so out of this, so from our characterization lemma, so it says that so regular toruses has the set G mod B S is finite collection of points, and also we have additional property that centralizer in B is of S is equal to the centralizer of G. Yeah. And centralizer also, the centralizer of G of S is should be contained. So we also proved that it is contained in any Borel subgroup. In any Borel subgroup. Containing S. So, and in particular, S is contained in T. Yeah? So, in particular, in any in any Borel subgroup containing T, so this is precisely the so the corollary that this is finite set, and actually it is equal to G mod B T for maximum torus T containing S. So for T containing S, and containing. And notice that this set of inclusions of centralizers, so this is a corollary that it is just a fixed point. So this is the orbit, so it acts on the component of the set of fixed orbit, and this is the stabilizer of the point in GS. So that's why you have one orbit point if and only if they equal. Yeah? So, and this condition is precisely the corollary, since this you see centralizer is the stabilizer of each point here. Yeah, so that the equality is also says that centralizer is the stabilizer. So since this holds for any B representing this finite set, components in the finite set. So just the stabilizers of this finite set is B, and this runs through this B here. I mean. And so what is said here that ZB, and in order to say that centralizer, so this thing fixes this point. So we were saying that this fixes particular this point, and stabilizing G mod B is precisely B tilde. So you have this kind of containment. So, and we are saying that this is parallel subgroup containing S. So since we have equality on this set of points, so this is also fixed point of T. I'm just recalling what we have proved out of this thing. And so you see that in particular, we see that this centralizer of G of T, of B of T is contained, and the G of T is contained in the I of T, yeah? And there is nothing to prove, yeah? So now we take this, so now we have, so now torus is singular. And so you have S is now the kernel of alpha, so it is some T alpha. Yeah, so actually you have to take connected component of the set. I forget to say this. Yeah, so this just now if you want to speak about centralizer, so yeah, notice that this is if and only if the torus is regular. Yeah. So just so since so this is not equal to centralizer. So since just otherwise torus is regular. And this allows us to say that you have so fixed point, and if the yeah, so G alpha, so G alpha intersects with B is just some B alpha. So we assume that alpha and lambda is positive. For some regular lambda. Yeah, so we can assume that this B is just B lambda for some regular lambda, and the condition that you have this particular B alpha is just saying that it is positive. Yeah? why do we really need this? In order to check that if your one parameter, something belongs to one parameter subgroup that has B alpha for one parameter subgroup which has negative pairing, then it won't contain B alpha. So that's what we wanted to state. And also we know that so since in this case we have reflection element and alpha coming from PGL2. This we have so alpha also, so root system delta corresponding to the composition complementary to I of t. It has it has both alpha and minus alpha. So a root system delta corresponding to this has both alpha and minus alpha. Yeah, because all roots are outside of I of t are obtained by this construction where these groups are not equal. Yeah, and this is of semi-simple. If you take it modulo t, this will make this group semi-simple rank 1. Yeah, so this is a trick. So that in the radical we do not know anything, but we are agreed to do this. But in this particular case where the root is outside of I of t, then your root is just different. Yeah? It has both I of t and minus I of t in its closure. So let us write it down, this symbolic picture. So we have weight 0. So we have weights that we do not care. So Lie algebra of I of t. So gamma delta. So we do not know nothing about this. Know nothing about these roots in I of t. And we have roots, so the Borel group containing I of t, yeah? And this p. And then also it contains some roots, alpha, beta, etc. And you can take G modulo B symbolically. I mean, it as a T this is G mod B, but I mean this is a complement with T equivalent complement. So that is T equivalent decomposition. And here you have negative roots. Yeah? Clearly, yeah? Because if so just because we decompose, so we fix B and we take B, and formally the opposite should lie, it's not in B. Yeah, so because B alpha, the opposite is not in B just because of it corresponds into B alpha minus. Yeah. Yeah, just because I mean, just because here we have the condition that if if B and so if they have common intersection root alpha, then the corresponding B alpha and B alpha minus would have the corresponding root, which is not the case, yeah? Because the decomposition is too small. And then the idea is to just instead of proving the normality, so we shall find, so aim is to find so normality is hard to prove because you should know something about action, yeah? So you should express some action. But here there will be a trick. So instead of normality, you can take, so aim to find H inside the unipotent radical of U. So maximum unipotent subgroup containing I of t I of t and having codimension 1 so it contains I of t and having a dimension I of t plus 1. So and also so we assume that it contains the corresponding so b alpha, this b alpha, yeah. So and also I and b alpha. So this will imply that it contains the corresponding root vector, and this so b alpha is precisely Borel subgroup centralizer, and since B is generated such B alpha, so yeah, so I claim that after that we shall have the following, that this condition implies, so this implies that that I of t is normalized by H, and since the H contains B alpha, automatically it is I of t normalized by B alpha, that generate B when alpha runs so together with previous ones, yeah. So just that generate the B with centralizers of tori that S is of codimension 1 and regular. Okay, and this we will finish the proof. Why this claim about normalization? So так, опа.
Ну да, тут еще вот предыдущая должна была быть 20-й.
Да.
Вот. А вот та должна была быть. А я следил, а просто в какой-то момент хотел вам сказать, но сразу начали говорить, и я как-то не успел. Я такой, ну ладно, чуть позже скажу.
Постеснялись.
Да.
Yeah, so this Yeah, so here you have this. So why this error follows? So claim is that H is not, so H is contained in U. So this implies that H is an nilpotent group. Yeah, and it will be connected. I mean, just because it is generated by two connected subgroups, yeah. So it will just I would say, yeah. So it will be clear from the definition that it will be connected. So it is nilpotent connected. So we have proved that normalizer of so if you have any proper subgroup, so for H tilde inside of H, we have normalizer of H tilde inside H is not equal to H. So it's not equal to sorry.
What is HT?
For any subgroup, so for any subgroup H0, yeah. So the normalizer of H0 is strictly larger. In nilpotent groups, you have to notice that the normalizer of this is induction by the on dimension. So this is very easy, straightforward thing, and also dimension. So this connectedness implies that the dimension of the normalizer is strictly larger than dimension of H0. So it's not, I mean, in nilpotent group you have the property that normalizer of subgroup is larger, but this can happen in finite groups, yeah? But here also important factor that if we start with H in nilpotent connected, then the normalizer will have larger dimension. And this will imply that, so since dimension of U is just, sorry, of I of t is just dimension of H is just dimension of I of t plus 1. So this implies that normalizer of I of t, so dimension of normalizer, so is equal to H. Yeah, so since dimension should increase. Yeah. Is bigger than dimension of I of t. Okay. So this implies the claim. So now we shall prove the claim, and we will finish. So the idea is the following. So we take H is a unipotent radical. So take H to be the unipotent radical of Borel subgroups of all B that implies lives in fixed points. So such that intersection with centralizer of T alpha in G is just our B alpha. So this, yeah, so since in order to do this, you will have, so this is an intersection. So to check this property, yeah? So this is an intersection of all Borel subgroups containing T. So notice that for Borel subgroup, for any Borel subgroups containing T, we have either the property that, so here we have two options. We have two options. Since in PGLN you have only two Borel subgroups containing maximal torus, one-dimensional maximal torus, then we have only two options that B intersects the centralizer by B alpha or B minus alpha. Yeah? So we have proved this. We do not have other choices. Yeah. So this this will show us that this is an intersection of B of T, so such that this is controlled via the pairing of one parameter subgroups. So such that alpha is lambda. So this is an intersection of B lambda U, so part B containing T. Yeah? So such that alpha, lambda and alpha has positive pairing. And so we have restated this condition in this setting. So if we claim now that so from H we can pass to the Lie algebra now. So H of course contains torus, I mean H itself, because sorry, H is not containing torus, but H is normalized by the torus, because it is intersection of Borel subgroups containing torus. Yes, so H is normalized by T.
And why it's not containing torus?
Yeah, because I have written the unipotent rate. Yeah. So it is just normalized by torus. So in order to check, here you have to check that weight space belongs to, so we have to check that G beta, so weight subspace, that so if you have G alpha that sits in H, so we notice that this property implies that beta, so this implies the property lambda alpha strictly bigger than 0. Yes, so you are taking this implies that you are so if beta is inside H, then beta appear. So claim just let me say it as the claim. So if G beta belongs to H, so that minus beta does not belong to H. So let us prove it with this kind of statement. So suppose beta is not equal to alpha. Yeah, so if yeah, so this is yes, so sorry, this is just because we sit inside B. Yeah, so now suppose beta is not equal to alpha, then if so this implies so since with the root you do not have opposite, so beta and alpha are not proportional. And if you have two non-proportional vectors, there is always so this is beta, this is alpha. There is always a regular hyperplane. So notice that you have the set of singular hyperplanes that are that is finite set. Yeah. So there is lambda corresponds to so then there is lambda corresponds to regular element, to regular one parameter subgroup. So such that beta, lambda of beta is negative and alpha of lambda is positive. So what does it mean actually? So that you have two vectors and you have a set of hyperplanes. So you have finite set of hyperplanes vanishing orthogonal to your vectors. So you throw them away, but still you can find a hyperplane so that divides your root system into, I mean, for which this is a negative vector and this alpha is positive vector. So this is just a linear algebra on the collection of vectors. So since the set of orthogonal hyperplanes is finite, so that we do not use. Where lambda for which lambda does not belong, is fine. And this implies now the following. So this the existence of such vector shows you that if you have B lambda, if you take this Borel subgroup, so you intersect it with centralizer of T beta in G. And notice that it will be negative. Yeah? So that correspond to the negative Borel subgroup. And H is inside B lambda. So since intersection is of B lambda and G T alpha is just B alpha by the condition of the pairing. Yeah, so this is since the pairing of lambda and beta is negative, and the pairing of alpha and lambda is positive. Yeah? So that intersection of B lambda. So that we have proved the following. So if your root is not, so we have totally proved the following. So if you have G alpha, which is in H, and so we have proved that if G alpha sits, G beta, sorry, G beta sits inside B, yeah, but G beta doesn't sit inside E of T. Yeah, so we have found so we have proved that G beta does not belong to H. So since opposite case occurs, so since B lambda intersection with G T of beta is B minus, that prevents to have beta, so G beta inside H. Yeah, so since potentially after that intersection we have G minus beta and not G beta. So that proves the claim. So we have found the, I would say, to have G beta, so since so this B lambda contains H, and this equality says that B lambda does not contain G beta. Yeah. So Lie algebra so this equality says that so we have proved that B lambda contains H, but we have found B lambda that contains H, but not containing this G beta. So G beta is not in the lambda, in H. So okay, so this proves the claim. So if what we have proved, that if your vector is inside, so it's a root vector of beta and not that is not inside the I of t, so we have put it away, and this means that we have only I of t and G alpha in the group. So the group is generated by I of t and E alpha. So since it is generated by so actually we could take connected component and this is so in order to take the group H. And so this tells you that, so since we analyzed the all root vectors, so it was what was not clear and what we were proving. I mean, if we knew that just adding the root subspace, so we have taken Lie algebra. We have taken Lie algebra of I of t and added G alpha to it. Yeah. So if you knew that G alpha normalized Lie algebra of I of t, and we can take the corresponding group generated by them, that will be precisely group H. But we made it in the other way. We have found the group, the definition for group H. We proved this explicit construction. And out of this construction, we have proved that its Lie algebra contains only I of t and complementary subspace G alpha. And this is it. So, thank you. So, it's all for today. So next time I plan to start speaking about geometric quotients and stability conditions. Помогите нас сохранить.